Yes. So this is Chapter 11 review. Number 1. An ice cream shop has 21 flavors of ice cream, 7 toppings, and 8 mix-ins. How many different sundaes can the shop make? So when you're given a question like this and you're asked how many different sundaes can you make, that means you're picking 1 ice cream, 1 topping, 1 mix-in. Yes?
Is this just like 21 and then plus the 7? What is it called? For what? Yeah, is that what the...
This goes back to the fundamental counting principle. We have 21 flavors. We're going to multiply by the 7 toppings, and then we're going to multiply by the 8 mix-ins. That's going to give us the total number of sundaes that we can make. So when we plug that in, we're going to get 1,176. So you can make 1,176 different sundaes. 2 and 3 should be fairly quick. Those are just punching them into your calculator, whether it's permutation or the combination. Remember that the permutation and combination key is under menu, probability, and they're right there. You enter these numbers in as an ordered pair, and it always goes bigger number, comma, smaller number. So you have 9, comma, 3. You plug that in, and you should get 504. So these two should be fairly quick on the common assessment. It's just plugging them in. Same thing for the combination. It's going to be 7, comma, 3, which is going to give you 35. Now, where it gets a little more challenging are the story problems that you're going to be asked, and you're going to have to determine whether they're a combination or a permutation. So in number 4, we're told 8 teams enter a tournament. In how many ways can the teams win first and second place in the tournament? So is this one a combination or a permutation?
Permutation.
Why is it a permutation? Because what?
There's places.
Because order matters, and order matters because we're assigning first and second place. So this one will be a permutation. So once you've determined it's a permutation, this should be a fairly simple problem. You have 8 teams, and you're picking first and second, so you're picking 2. So when you plug this into your calculator, you should pick the permutation, and it should be 8, comma, 2. Which is going to give you 56. Number 5. In how many ways can 8 performers be listed in a program? What kind of problem is number 5? It's 8 factorial. Remember, oftentimes if you're only given one number, you should automatically think that's a factorial. And it makes sense because we have 8 performers to begin with. Once we've listed 1, we have 7. Then we've listed another one, we have 6, and so on. And that's what a factorial is. It's 8 times 6 times 5 times 4, and so on. So this is 8 factorial, which gives us 40,320. Number 6. How many ways can 4 DVDs be borrowed from a collection of 25 DVDs? Combination or permutation?
Combination.
Why?
Because there's no order. It doesn't matter what.
So it doesn't matter which 4 DVDs we pick, and it doesn't matter which order we pick the 4 DVDs that we pick. We're just picking 4 DVDs. So this is a combination. Our total number of DVDs is 25, and we're picking 4. So again, that should be fairly simple, just plugging it into your calculator. It'll be the combination 25, comma 4, which is going to give you 12,650. So that's combinations, permutations, and the fundamental counting principle. Now we're going to move into our probability stuff. So number 7. A spinner is numbered 1 through 10 with each number equally likely to occur. What is the probability of obtaining a number less than 2 in a single spin? So we're given the numbers 1 through 10, so I like to list them just so I can see them all. So we have the numbers 1 through 10. We want to find the probability of obtaining a number less than 2. So how many numbers do we have that are less than 2? Just 1. And that's out of how many?
10.
So our probability is 1 out of 10. Remember that a probability is the part over the whole. So this was the part that we were looking for over the whole. We have 10 digits total. So that one was just finding a single probability. Number 8 is our geometric probability. You will not be given the area of a circle on the common assessment, so if that's something that you don't remember, put it on your half a sheet of paper. Area of a circle is pi r squared. So for number 8 it says, if one point is randomly selected from the points inside the rectangle shown below, find the probability that the point is in the circle. So remember that geometric probability is still your part over your whole. So we're interested in the circle. So we're going to have the area of the circle, and we're going to divide by the whole, which is our total area, which in this case is the area of the square, or the rectangle. So we need to find the area of that circle. And how do we find our R value? We're not given an R value, so how do we find it?
Divide them 12 and
So we cut the 12 in half because we realize that our circle goes from edge to edge on our rectangle here. And we know that the R value is our radius, which is 1/2 of that distance. So we know that we half that 12 and we get 6. So we should get pi times 6 squared, which gives us 36 pi. Or if you multiplied that out, you would get a larger number. If you multiplied the pi out, which is fine. Then we need to find the area of the rectangle, or our total area. So how did we find the area of the rectangle?
Base times height.
It's length times height, or length times width. Or in the case of a square, it's side squared because the sides are all equal, so you'd have side times side. And in this case it is a square, so we would have 12 times 12, which equals 144. So then plugging that into our geometric probability equation, we get 36 pi over 144. And when we actually plug that into our calculator, you should get 0.785. And then if we made that into a percentage, remember that we're moving that decimal 2 places to the right. So we get 78.5%.
Can we do 79%?
It'll depend on what the common assessment says. If it has it rounded to 79, then yes, it would be 79%. If they have 78.5, then it would be 78.5%. So it's going to all depend on what your choices are in the multiple choice. Number 9, define what a mutually exclusive event is. Now, on the common assessment, you're not going to be asked to define what a mutually exclusive event is. You're going to be given the 4 choices for your multiple choice, and you're going to need to pick the mutually exclusive event. So if you can define what a mutually exclusive event is, you should be able to pick out which one of the events is mutually exclusive. So what was a mutually exclusive event? What did it mean to be mutually exclusive?
Like it can both happen at the same time.
For mutually exclusive?
No, it's no.
For a mutually exclusive event, they're completely separate events. They cannot occur at the same time. So when we talk about mutually exclusive, it's two events that cannot happen at the same time. So that's the important thing about mutually exclusive. So then on to the next page, we move into finding these mutually exclusive or inclusive probabilities. Remember that they were the ones that have the or. Mutually exclusive and inclusive are your or problems. And on the common assessment, they will be capitalized like this. They want you to see that or. It's a clue. So for number 10, each of the numbers 1 through 9 is written on a card. The cards are placed in a stack and one is drawn at random. You want to find the probability that the number is a multiple of 3 or is even. So again, I like to see my numbers. And then I can mark on them and I can see if there's that overlap or if they're completely separate. So, numbers 1 through 9. Find the probability that it's a multiple of 3. So multiples of 3 start at 3, and you're going to count 3. 1, 2, 3. So 6. 1, 2, 3, 9. So those are your multiples of 3. So the probability of getting a multiple of 3 is 3 out of 9. And then what did we do for our mutually exclusive and inclusive probabilities? What was the operation that we did?
Plus them.
We added them. So we're going to add now the probability of getting an even number. Our even numbers are 2, 4, 6, and 8. So we have a 4 out of 9 chance of getting an even number. And now, for your mutually exclusive and inclusive probabilities, you need to ask yourself, are any of my multiples of 3 even?
Yeah.
So that's where making these marks helps. Do I have a little line and a bar underneath one number or under a couple numbers? And I do,
Yes.
under the 6. So what do I do with that 6?
Subtract.
I subtract the 1 out of 9 possibility of getting that number.
So would that just be exclusive? Like,
So this is an inclusive problem because you have that overlap. So when we combine these, we're going to get 6 over 9. But remember, we want a reduced fraction. And when you plug this into the Inspire automatically gives you the reduced fraction. So you're going to get 2/3. Number 11. A standard die is rolled. Find the probability that on a single roll, an even number or a number less than 4 is rolled. So on a standard number cube or on a die, you have numbers 1 through 6. We need to find first the probability of an even number. So that's 2, 4, and 6. So that's 3 out of 6. Or a number less than 4. Our numbers less than 4 are 3, 2, and 1. So again, this is an or, so we're adding 3 out of 6. And then did we have any overlap? Did we have any even numbers that are less than 4?
Mm-hmm.
We had 1 right here at 2. So we're going to subtract that 1 out of 6 chance of rolling the 2. So we're gonna get 5/6. Number 12. Unfortunately, where I didn't write the common assessment, there are going to be card problems. If you do not know what it's asking or how many there are of something for the card problems, ask me. I'm more interested in you being able to do the mutually exclusive, inclusive problem than knowing how many diamonds are in a deck of cards. It's something good to know, but if you don't, ask me. I will tell you. Ask Miss Audia, she'll tell you. Ask Mr. Duke, he'll tell you. It's more important that you know how to do the probability. So in number 12, we're told that a card is drawn from a standard deck of 52 playing cards. What is the probability that the card is black or a diamond? So first we need to find the probability of getting a black card. In a standard deck of cards, half of your cards are black, half of your cards are red. So if half of your cards are black, half of 52 is 26. So you have a 26 out of 52 chance of drawing a black card. Or a diamond. So again, we're adding, because we're still looking at the mutually exclusive, inclusive problems. And we need to know the probability of getting a diamond now. There are 13 diamonds in a deck of cards. There are 13 of each suit. So 13 spades, 13 clubs, 13 hearts, 13 diamonds. So we have a 13 out of 52 chance of drawing a diamond. Now, can a black card also be a diamond?
Yeah.
No, a diamond is a red card.
Oh.
So you can't have a black diamond. All of the diamonds are red.
We'll just bring a deck of cards.
Yeah, no, I don't know anything about
Are there other problems?
There are going to be card problems. So here we don't have any overlap.
So that's mutually exclusive.
So this is a mutually exclusive problem. So we're going to add these, and you're going to get 39/52, but if you do it on the Inspire, it'll reduce it for you, and you'll get 3/4. So your reduced fraction should be 3/4. And then number 13 is our last mutually exclusive, inclusive problem. It says a bag contains 8 blue marbles, 5 yellow marbles, and 2 green marbles. We need to find the probability of drawing a yellow or a green. So this is not to be confused with when we were picking 2 marbles and we were putting them back. This is talking about picking 1 marble, and they want to know what the probability, when you draw that 1 marble, what the probability of is getting a yellow or getting a green. So this is still a mutually exclusive, inclusive problem. So we need to find the probability of drawing a yellow. And there are 5 yellow marbles. And that's out of 8 plus 5 is 13, plus 2 is 15. So we have a 5 out of 15 chance of drawing a yellow. And then we're going to add our probability of drawing a green. We have 2 green out of our 15. Now, can you draw a yellow and a green marble at the same time if you're only drawing 1 marble?
No.
No, so this one doesn't have any overlap either. So we're just going to add these, and you're going to get 7 out of 15. Now, number 14 is moving into independent and dependent probabilities. And 14 asks you to define what a dependent event is. Again, the common assessment is not going to ask you to define it, it's going to ask you to pick out which one is dependent or which one is independent. So as long as you can define it, you should be able to pick out the event that is dependent. So what did it mean to be a dependent event? So what? So your second event relies on what happened in the first event, or your second event depends on the first event. So one event affects how a second event can occur. So basically, your second event depends on what happened in your first event. So that's what this next set of problems is going to focus on. So number 15. A bag contains 3 white marbles, 2 red marbles, and 7 blue marbles. A marble is picked at random and is replaced. Then a second marble is picked at random. What is the probability of drawing a white marble and then a red marble? So the key words that you want to pay attention to in the independent and dependent problems are replaced, not replaced, without replacement, with replacement. Those are the words that you're looking for. Those are going to tell you whether it's an independent or a dependent event. So in 15 it says that we're replacing the first marble that we chose. So does that mean we're independent or dependent?
Dependent? Or no, independent?
Independent, because we're replacing. So we're not, after we draw that first marble, we're not changing our set because we're putting it back. So we still have the exact same set that we started with. So for number 15, we need to find the probability of drawing a white marble. We have 3 white marbles, and that's out of 3 plus 2 is 5, plus 7 is 12. So we have a 3 out of 12 chance of drawing a white. Then, what's the operation that we do for independent and dependent?
Multiply.
We multiply. So we're going to multiply by the probability now of drawing a red. Well, we have 2 red marbles, and we replaced that first marble, so we still have 12 marbles. So when you multiply this, you should get 1 out of 24 for your reduced fraction. And again, you can just plug this into the Inspire and it will reduce it for you.
You don't need percent.
No, on the Common Assessment, you'll most likely be asked for the ratios. Number 16, suppose that 3 coins are tossed. What is the probability that 2 will turn up tails and 1 will turn up heads? So in this case, we're tossing 3 separate coins. Each coin is independent of of all the other ones. So each toss is independent of the others because you're tossing 3 separate coins. So these are all independent events. And we need to find what the probability of 2 turning up tails is and 1 turning up heads. So what's the probability of getting a tails on a coin?
2.
It's half. You have a 1 out of 2 chance, right? Because you could get a heads or a tails, and you want to get a tails, so that's 1 out of the 2 choices. So you have a 1 out of 2 chance of getting a tails, and then you want to get a tails again. So we're going to multiply by 1/2 again. So that's the probability of getting 2 tails. And then we want to know if 1 turns up heads. Well, what's the probability of getting a heads? 1/2. So again, we're just going to multiply by 1/2 again. And that's because each of these coin tosses is independent of the other. You have a 50-50 chance of getting a heads or a tails no matter what. So when you multiply this through, you get 1/8. Number 17. Consider a drawer that contains 6 black socks, 4 brown socks, and 8 white socks. 1 sock is taken at random and not replaced. What is the probability of drawing a white sock followed by another white sock? Is this an independent or a dependent problem? It's dependent because we're not replacing that first sock that we drew out. So we need to find the probability of drawing a white sock. Well, there are 8 white socks to begin with. And that's out of 6 plus 4 is 10, plus 8, so there's 18 total socks. And again, this is independent dependent, so we're multiplying. And now we want to draw another white sock. So we drew a white sock in the first draw and we didn't put it back. So how many white socks do we have left? 7. And how many total socks do we have left? 17, because we picked out that first sock and we didn't put it back. So both of these numbers go down by 1.
Dependent.
This is dependent. So we're going to multiply, and you're going to get 28 over 153. That is the reduced fraction. For number 18, Joe has 4 black ties, 1 purple tie, and 6 gray ties in his dresser drawer. If he selects 3 ties at random with replacement, what is the probability he will select a black one first, purple one second, and gray one third? So this time we're picking out 3 different ties. Is this an independent or a dependent problem? Why? Because we're replacing. So this is an independent problem. Each probability will be independent of the other, because we're putting back the ones that we took out. So the probability of getting a black one first, he has 4 black ties. Out of 4 plus 1 is 5, plus 6 is 11. And then we're multiplying by the probability of picking out a purple one. There's 1 purple out of his 11. And then finally picking a gray one. There are 6 gray out of the 11. So we're going to multiply all 3 of these fractions. And we're going to get 24 over 1,331. There will be one on there like this, that you're multiplying more than just 2 fractions. That you have to do more than just 2 probabilities. So be aware of that. And then number 19. In a game, a player tosses a die and chooses one of 26 alphabet cards. What is the probability that a player gets an odd number on the die and then C, J, or R on the card? So we're rolling a die and we're picking a card. Are these independent or dependent probabilities? They're what?
Independent.
They're independent. Rolling a die and picking a card are 2 completely separate events that don't affect each other.
You said it's what?
These are independent events, rolling a die and picking a card. Because whatever you roll on the die will not affect what card you draw. So we need to find the probability of getting an odd number on a die. So there are 1, 2, 3, 4, 5, 6. Those are the numbers that you could get on a die. Your odd numbers are 1, 3, and 5. So you have a 3 out of 6 chance of getting an odd number. And then we want to know the probability of picking C, J, or R out of those 26 cards. So there are 3 different cards that you could pick out of the 26.
Wait, so you're only picking 1 card, or you're picking
You're only picking 1 card.
3 different cards?
You're just picking the 1 card, but your 1 card that you pick could be a C, a J, or an R.
Oh.
Okay? So then we're going to multiply these through, and your reduced fraction should be 3 out of 52. On the next page, 20 through 23 deal with the information that we're given here. We're told that event A is that when you roll a die, you get an odd number. And event B is whether you roll a 3 or a 4. And this wants you to write your probabilities as an unreduced fraction. So for 20, we want probability of event A. So again, our numbers are 1, 2, 3, 4, 5, and 6. And we want to know the probability of event A, which was getting an odd number. So that's 1, 3, and 5. So probability of event A is 3 out of 6. Probability for event B. Event B is that you roll a 3 or a 4. So you could roll a 3 or a 4. That gives you a 2 out of 6 chance. 22. The probability of event A and event B. Now this one, do not overthink it. It's not going back to independent and dependent. This is asking you, with this problem, if you have odd numbers that are also a 3 or a 4. So do the two events happen at the same time?
No.
Yes, one time.
So it'll be 1
They
out
do.
of 6.
We can have that 3 is odd and it's a 3 or a 4. So you have a 1 out of 6 chance of having A and B happen at the same time. That's all that is looking for. And then 23 is our conditional probability. If you don't remember what conditional probability is and you can't remember the formula, write it down on your half a sheet of paper. Conditional probability is the probability of A and B divided by the probability of A. That's why we found these, so that you could plug them into your conditional probability. So we just found the probability of A and B was 1/6. That's going to be divided by the probability of A, which we found to be 3/6. And you can plug this complex fraction into the Inspire, just using the fraction key over and over. And you should get 1/3. So know how to do that conditional probability, what that conditional probability stands for, and what it means. Now we're moving into the stuff that was covered on the most recent test. We're moving into the mean, median, and mode, the quartiles, the minimum, the maximum stuff. Your sets on the common assessment will be about this length. They will be longer than they were on the test, so be aware of that. So 24, 25, and 26, we have to find the mean, the median, and the mode. If you have issues remembering which is which, put it on your half a sheet of paper. The first thing you want to do when you're given a set of data is make sure that you order this from smallest to greatest. And where these are going to be longer, cross out the numbers as you write them to make sure that you have them all listed properly. I would hate for you to get the problem wrong because you happen to miss one number. So that should be your set listed in increasing order. So now, for 24 we have to find our mean. What is our mean? Our mean is x bar, okay. How did we find the mean? We add all of our data values and then we divide by how many we had. So in this case, when we add them up, we get 1,026. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. So we're going to divide by 11. And we're going to get 93.3. So our average or our mean is 93.3. 25, we need to find the median. What was the median? The median is our middle number. So I showed you guys on Friday that I like to take my fingers and just move in one each time to help me find the median. So in this case, we end up at 97. Remember that if you have two numbers, if you're doing this and you ended up with like those two numbers, remember that you have to average those two numbers to find your median.
What happened
And then number 26 is finding the mode. What was our mode?
to the most sleeping?
The mode is the most common number, so the number that occurs most often in our set. So in this case, it's 97 again. Remember that if there are more than one numbers that occur the same number of times, and that's the most often occurrence, then you could have two modes. But it's always the number that occurs most often. Alright, number 27. We're given a new set of data. We need to find the minimum and the maximum. And then for 28, we need to find the quartiles. So again, we want to order our set from smallest to largest. And like I said, unfortunately, you are going to be given bigger sets like this on the Common Assessment. So take your time when you're ordering these sets. So that's going to be the set in increasing order. So for number 27, if we need to find our minimum, remember, is our smallest value. So in this case, it's 42. And then we need to find our maximum value, which is our largest value, which in this case is 62. Now we need to find the values of the quartiles. Remember that the quartiles are your Q1, your Q2, and your Q3. If you don't remember which is which in those, put it on your half a sheet of paper. Remember that Q2, what is Q2? Is the median of the entire set. Q1 is the median of the left-hand side. And Q3 is the median of the right-hand side. Remember that these are all medians, so they are all the middle numbers. So out of our set, we want to find Q2 first. We want to find our middle number. So this time we have two numbers, so we have to average those two 50s. And when you average the same number, it comes out as the same number, so that should save you time, that you don't actually have to do this. 50 plus 50 divided by 2 just gives you 50 back. So your Q2 value is 50. Now we need to look at our left-hand side. Now, where this 50 was the average of these two, technically our median for our entire set is right in between those two numbers. So when we look at our left-hand side and our right-hand side, we're looking at everything, for the left-hand side, everything to the left of that dotted line. For our right-hand side, we're looking at everything to the right of that left-hand side, or of that dotted line. So in this case, we're going to include the 50s that we averaged. So to find the left-hand side, we'll do the same thing. And this time we end up with the 245s. So again, when you average the same number twice, you get the same number. But just to show you, you'll get 45. So our Q1 value is 45. And then our Q3 value, we're gonna look at the right-hand side and do the same thing. This time we're averaging 52 and 55. So we have 52, oops. We have 52 plus 55 divided by 2 is gonna give us 53.5. So those should be your quartiles. Number 29 asks you to find the interquartile range, or the IQR value. Remember that your IQR value is Q3 minus Q1. So those are the Q values that you just found. So in this case, it's 53.5 minus 45. And that's going to give you a value of 8.5. Now, for number 30, on the common assessment, you're not going to be asked to draw the box and whisker plot. You are going to be asked to pick out the correct box and whisker plot. So as long as you know where all the values on the box and whisker plot go, you should be able to pick the correct box and whisker plot that's given to you in the multiple choice answers. So to create your box and whisker plot, remember that you're graphing the 5-number summary, which is your maximum, your minimum, and then your 3 Q values. So in this case, I numbered by 2s. So our minimum value was at 42. Our maximum value was at 62. Our Q1 value was at 45. Our Q2 value was at 50. And our Q3 value was at 43.5. The box is formed by your Q values. And then the whiskers extend out to your maximum and minimum. So you would get a box that looks something like that. Now, number 31. 31 is what we talked about on Friday. That it says what percent of the data is between Q1 and Q2. So this goes back to figuring out how much of your data is in each quarter of your box and whisker plot. Remember that you have 100% of your data is in the box and whisker plot. And it's broken up into 1, 2, 3, 4 sections. So if you divide 100 by 4, you get 25. So 25% of your data is in each section. This section is worth 25. That section is worth 25, that section is worth 25, and that section is worth 25. So Q1, remember, is the end of your box. Q2 is the middle of your box, so it's asking for just one section. So that's 25% of your data. If it asked for how much was between Q1 and Q3, you would have 2 sections. So that would be 50% of your data, because it would be 25 plus 25. Is everyone okay with that? How your data is broken up? 32, it wants you to name any outliers in the following data. So again, the easiest way to do this is to order your data. Yep, I got it. Thank you. I appreciate that. 6.0. Okay. Now, it gives you a hint that you should calculate the lower and upper bound, which is the upper and lower fence. Now, that's going to take finding the Q1 value, finding the Q3 value. You have to find the Q2 value so that you can find the other ones. It's going to be fairly obvious if there's an outlier. If we look at this set, which number is not even close to any of the other ones?
0.1.
This 0.1 is not even close to the nearest number, which is 4.4. So you're safe to assume that that's going to be an outlier. It wants you to find the lower and upper bounds, but if you're crunched for time and you do not have time to find the lower and upper bound, pick the obvious answer. It will be clear. So in this case, it is 0.1 is your outlier.